I've asked you to call up your AnyLogics and have them fired up to go. And that's because we're going to have a busy day today talking about two levels of issue. One of the issues concerns how we represent spatial embedding for agents. And we'll start to get into mobility a bit, although I'll ask you to review a video more on that. How do we situate agents in space, as we talked last time about situating them in a network? This is one type of problem, one type of issue. And the lecture will show some examples of agents embedded in space in different ways. The second issue, though, is a little bit deeper. And it's a high-level point that will occupy less of our time, but has even more significance. And it's this idea of stylized models. Models that are in some ways caricatures of the way the world is. They're not designed to depict an exact situation. They're not designed to help you decide in very quantitative terms between the impact of doing A versus B. But instead, they're thinking prostheses, as my colleague Jeff McDonald calls them. They're ways of helping us reason through consistently the implications of our theories about how things are in the world so we can more quickly learn. We can more quickly debug how we understand the world. Some of you folks may have heard this whole notion of fail early, fail often. The idea is not to make mistakes, deliberately. It's not to be careless or cavalier, but it's to not be afraid of trying things, experimenting and failing, because that's how we learn often. That's how we most learn. And obviously, there's limits to some of this, but these models are examples of this class of stylized models, which are designed to give us insight. They're designed to help us think more thoroughly and more quickly through our assumptions about how things work out there in the world so we can debug the problems. If a model fails to match up to real-world data, that's not a failure. It's not something we should be ashamed of. It's not something that we should think as a real letdown. It's actually where we've gained something valuable. We've learned how we are thinking it may work doesn't add up. It doesn't jibe with what we see in the world. And now that can help us revise our understanding about how things are working out there in the world. So we can think more clearly, more consistently, and more quickly using these sort of models. Falls into the notion of models as thinking tools. And I think the notion of thinking prostheses. What do I mean by a prosthesis? Anyone? Give me an example of a prosthesis. Yeah, a crutch. Some people who have lost their legs will have replacement artificial legs, artificial feet. They'll have an artificial hand. They help us extend our range of movement, what we can undertake in terms of activities of daily living in ways we wouldn't be able to otherwise. And models are like that for our thinking. They can help us think through, models can aid us in our day-to-day thinking, is part of the idea here. So these sort of stylized models, they're caricatures, as I said. They're not meant to depict the full richness of the world. Rather, they're meant to sort of depict essential aspects that, and often there are interactions, that will help us understand real-world phenomena or help us understand the implications of several things interacting in unexpected ways. So they're aimed at stimulating insight, not necessarily quantitatively help us choose A versus B, but help us think through, could the pattern we see in the world be plausibly explained by this certain type of interaction? Or suppose you have this type of interaction, what's the implications of it for what we'd expect to see in the world? It might motivate us to go collect some data, might motivate us to sort of refine our understanding about the way things work. So they abstract away from a lot of details, just like a caricature does. You know, you've seen those political cartoons where they'll draw a prime minister with a giant chin or a giant nose or a big head or what have you. And of course, that's not how exactly the person looks, but it captures an essential truth. It captures sort of an essential feature of the situation. And so it is with these models. They help us think consistently. And today, ladies and gentlemen, we're going to see two of the most famous agent-based models out there that are stylized models. Okay? Two models that have really made a difference for how people think about things in one way or another. They're quite different models, but they're going to be simple, and they're going to be making use of spatial context, and in fact, in one case, mobility, embedding things spatially. So this lecture is going to be talking about stylized models. It's going to be talking about spatial embedding, and it's going to be operationalizing them in AnyLogic. And so I want to comment a little bit on AnyLogic and its spatial embedding types. Why do we care about spatial embedding? Well, spatial embedding of agents, these individuals interacting in a model, is essential for certain types of things. For example, if we want to capture a locality of influence, that one person near another influences them, maybe they influence them by spreading ideas, rumors. Maybe it's by transmission of pathogen. This sort of spatial embedding can also allow for understanding buildup of environmental pathogens, things in the environment, the contaminants of various sorts, biologic, chemical. They can help understand how things travel from one place to another, and can help us understand the origin of sort of patterns we may see in the world. Maybe it's cracks in the way they propagate in ice on the South Saskatchewan River. Maybe it's concentric circles we see, or the shapes of sand dunes. They can help us understand these things by mapping things out spatially. And that's harder to do, ladies and gentlemen, in a stock and flow model. Often we'll let the stock and flow model represent a given area, but you can't really get the level of fine-grained resolution to recognize the shape of a sand dune as easily there. We can't understand why we see in rabies these kind of patterns of infection spread which go in concentric circles and travel outwards. We saw that in the very first day we're using these agent-based models, these kind of expanding rings. And we can capture that via spatial embedding. And finally, spatial embedding can permit GIS integration. Anyone know what GIS is? Just talking to our department head about be really nice if we had stronger representation of GIS in computer science courses, because it's a huge area. Yeah. What is GIS? Yeah, or geographical information systems. So it's systems that are computational in nature, but they maintain information about geographically mapped points out there in the world. So geographically mapped data. A lot of data is geographic. Where people get sick. They get sick somewhere, right? Where they go to school. Where they live. There's a lot of phenomena that are geographic in nature, and it has implications. Whether you can walk to school or whether you have to take a bus or some other vehicle. Whether you can bike, whether there's a bike path nearby. So it turns out there's this whole area of information systems, of computational support to give insight in the area of geographical data. So AnyLogic supports three types of spatial embedding. And we're going to be glossing over the first one today. We'll see it a lot more, and you'll see it in a video I ask you to watch before the next lecture, continuous embedding. We've actually seen that already. We saw that in the last lecture, we could distribute people in space. We could put them in a ring, for example. And you'll be seeing more of that in your problem set and for next week. So continuous embedding, here individuals are placed in space, latitude and longitudes, physical locations with them. So you can map out, you know, the location of a hospital and clinics and which people go to which ones, and put it in a context of streets and traffic and the context of limited accessibility across the river or what have you. Finally, and this is the one we're going to concentrate on today for the sake of this lecture, we're going to be talking about discrete cells. We divide up a space. In fancy terms, we tessellate it. We subdivide it in a way that's mutually exclusive and collectively exhaustive. In other words, every point is in some square in this case. The squares cover the entire space and they don't overlap. They're mutually exclusive. You're either in one square or another. Okay? And here, there's actually a physical occlusion. Only 0 or 1 agents are present in each of these patches, these squares. Okay. The AnyLogic class, if it has agents within it, like main has agents within it, it'll be setting the parameters for the nature of the 2D landscape. The width, the breadth of the space, whether it's continuous or discrete, and then for discrete spaces, what's the neighborhoods by which people are considered surrounded? Is it those in the 4 cardinal directions, north, south, east, west, or is it in a broad set of directions, northeast, southwest, and 8 different surrounding cells? So let's take a look at this, okay? I'd like you to load in a model called Wandering Elephants, okay? And this will be, a very first model we'll just be glancing at today. To do that, go up to the Help menu and call up Example Models. And when you call up the example models, you should see something like this on the right-hand side. And I'd like you to, and it's unfortunately, you can see it on the screen up there. I can't see it on my screen, so I'm going to have to crane my neck. But there's a thing called Wandering Elephants down here. Do you see that? Wandering Elephants. It's on the right-hand side here. And if you don't see it, you may want to click this Examples over here, and it will make sure you're in the right area. But it's Wandering Elephants, yeah? Okay. So call up Wandering Elephants by clicking on it. You click on the link that's next to it, okay? And this is going to load in this model. Now, here what you'll see is that we have elephants represented. Each of these is, so double click on elephant on the left-hand side. And each elephant is represented as associated with a state chart that captures their behavior over time. And their behavior, as you can see, is quite stylized. They wander around, they pick new directions over time, and then at some point they get thirsty. By the way, this is a hierarchical state chart, so we actually have a bigger state and a substate within it. You can do that within AnyLogic, and that's fruitful to do that sometimes. Here's this got thirsty, so they need water, so they'll go to water, and then once they drink it, they'll start wandering again. Very simple little lifestyle that's depicted. Let's go run this. So right-click on the simulation there. Okay. So if you right-click on the simulation, you can choose Run. Okay. And we're going to run this thing. So here are elephants, right? Elephants are moving around this space. They're zipping around. And elephants that are red, in this case, represent thirsty elephants. So they'll be often making a beeline for water. So these elephants are moving around. Here we're just depicting things by the altitude of the elephants, but we can actually display vegetation here. And what you'll find is that in this case, the elephants, if we speed things up, they're eating away the vegetation, right? They're destroying vegetation in their tusked fashion by eating it and pushing it, etc. And so they're eating away vegetation. The vegetation recovers over time, but it's in this kind of interplay with the elephants. And if we increase the volume of the set of elephants, we'd see a diminution of the amount of vegetation. Let's go back to the main area here, and I'm going to display this vegetation from the start, and you can see them really eating away at it. The vegetation decreases over time. So each of these elephants is its behavior is described by this notion of elephantness, characterized here. It has a period between when it needs to drink, something that tells if it's thirsty, gives its heading, the direction it's in, and something that governs its behavior. But these elephants, importantly, are located in a continuous space, meaning they're at a certain location, X and Y is given by a real number. Okay, a rational number. 32.5 in the X direction and 52.379 in the Y direction. And they move around. I'm running it really, really quickly, but if we slowed it down, we could see they're running more general direction. What's notable here is the elephants don't collide. In fact, in this model, they don't interact at all. We have other models like it, where we simulate deer populations here in the province, where they actually interact with each other. A male sees a female and will go after her or what have you. Males will hit their heads and so on, and stick each other with antlers in their male-like fashion. But these elephants, they're moving around and they don't actually interact. They can cross paths and there's no problem between them. There's no exclusion of one elephant from another elephant. So this is continuous space, and that's a feature of continuous space. The idea is we're looking at it, it's almost like we're in a plane, and we abstract away from whether cars collide. We just consider, the flow of elephants in one way or the other without dealing with if they have to go around each other. The elephants are very small compared to the space, so we consider their paths as being able to cross without problem. Okay? Elephants. We're going to be seeing more about this in the video you folks will be watching about how you can move these things. They're like sprites. You can tell them, go towards this place with this speed, and it will just take care of processing along. You actually don't have to advance them. So that's wandering elephants, okay? Continuous space. Pardon me. Okay, sorry about that interlude. So what I'm going to do is I'm going to go to Help, Example Models, and then I'm going to scroll down on the right-hand side and go to the game of life. Okay. So the game of life is a distinguished early example of what's something that arguably is an agent-based model. More specifically, it's what's called an automaton. Okay, it was invented in the 1970s by, I think it's John Conway, a mathematician in England, using ideas drawn from John von Neumann. Does anyone know John von Neumann's name? John von Neumann was a towering figure across multiple domains through about the 1950s, when he tragically died from brain cancer, I think, or earlier in his life, or in his 50s, I think. He was a remarkable contributor in computer science. Where have you heard the name von Neumann before? Yes, von Neumann architecture. It's the architecture where you have a CPU, central processing unit, and you have memory, and the processor gets data from memory. But he contributed across a wide variety of domains, including elements in economics and representing decision-making in the physics area, mathematics. He was also a mathematician, but had this incredible ability to contribute across different areas. He was also famous for working with what would be called non-von Neumann architectures, namely architectures which don't have a central CPU, but where processing is distributed. And that's what we're going to see here. It's the idea of a cellular automaton. Space is divided up into cells. We have discrete space, the cells, in discrete time, and it evolves over time with each cell reasoning locally about what's going on around it and making decisions accordingly. There's no central decision-making unit. Rather, the cells are independently evolving. The inspiration for the game of life is the life course of cells. The idea is that each of these patches will have will either be associated with a live cell or they'll be empty. And there are rules that govern whether a given empty cell is colonized by another cell, and whether an existing living cell lives or dies the next round. Okay? So this is a cellular automaton, and it's a class of very popular models for simulating the evolution of systems, whether it's lattice gases with lattice gas models, models of gas particles, molecules bouncing off each other, or whether it's biologic cells. It is deterministic. In contrast to almost all models we're going to be examining here, there's no uncertainty. There's no stochastics. Instead, it's completely fixed according to the rules. Given the initial state, it will evolve in a certain way. And what's notable here is that the game of life, it can exhibit the emergence of profound complexity from very simple rules. And it's actually computationally universal. Can anyone tell me what that means? I say it's computationally universal. I'll put it another way. It's Turing complete. What does that mean? Anything that can be simulated on a computer can be simulated in the game of life. Any computer program that you could create can be run in the game of life. You can create a computer in the game of life that will simulate anything that you could run on your fastest supercomputer out there. Now, it won't necessarily run as fast. It won't be as elegant to program it. You're not going to be programming this thing in Python probably, but it will run. So let's go run this thing. So, ladies and gentlemen, once you've loaded it in, right-click here and do run, okay? And we're going to take a look at this model. Now, this introductory screen actually says what the basic rules are for this model. And I'm zooming in with my mouse, and I'm right-clicking on it to move around, okay? So the rules are given here. And remember, each patch of this thing, we'll take a peek at it, each patch is either living or dead, okay? Living or empty. And to go back to these rules, if it's empty, if it has exactly 3 neighbors, 3 living neighbors, it will be colonized and come to life. The neighbors will sort of spread into it. Okay? If it's a living cell, if it has fewer than 2 neighbors, it dies of loneliness. It doesn't have enough cells around it to support it, to maintain a sort of a living environment. If it has more than 3 neighbors, then it will die of crowding. And if it has exactly 2 or 3 alive neighbors, it stays alive. And I should note that this is in a space that's called I believe it's called Euclidean space. So here, you can imagine space is divided up into cells. We're considering this cell, which are its neighbors? It's the ones around it, these 8 neighbors around it. Okay? Those are the 8 neighbors it considers. If there's 2 or 3 of them, and this one is empty, 2 or 3 of them, and this one is living, the central one, it continues living. If there's more than 3 around it that are living, think about pollutants being created, contaminants in environments, and it dies off, etc. If this thing in the center is empty, but there's exactly 3 around it, it will be colonized. Okay, so let's run this thing. What are the logical implications? Well, here's a patch, and you'll notice that things are evolving over time. So according to these rules, step by step by step, you see each of these cells evolving. cells that are living are shown in red. Cells that are empty are shown in yellow here. And you could see them evolving. Some evolve for a while and then are in a period of stasis. Some keep on changing. Anyone know what the name of this one is? Sorry? It's a blinker. Yeah, exactly. This one has a name too. I don't remember what it is, a block or something. Each of these sort of stable forms has been named in years long ago by people who played this hour after hour. And it was said at one point, I think in the 1970s, this game was responsible for more CPU time than any other program that had ever been written. People would spend massive amounts of time, and people analyzed this. And you could speed this up in AnyLogic so it goes fairly quickly. And what you'll find is that after a while, things, in a small space, things tend to settle down to some simple repeating patterns. Now, if you go and you click on things, like let's click next to this guy here. I'm going to click right in this corner thing here. You can get really interesting things going on that proceed in non-obvious ways. Here is a glider. It was just gliding around, and it ended up crashing into something else. But these forms have behavior associated with them that isn't always obvious. Now, from this sort of substrate, it turns out you can build a computer. If you're determined, you can figure out how to represent AND gates or NAND gates in this sort of world, in which case you could build up a computer. But people looking at this game tried to derive sort of broad rules, broad understanding of how it evolves over time, in addition to looking on it as a computational structure. So this is an example of a cellular automaton again. Each cell evolves over time, interacts with its neighbors in a local fashion. It's interacting purely locally. It's in discrete space, cells, discrete time, step by step by step by step, not continuous time in some gradual way. So, game of life, you can have a lot of fun with it. You could change the rules if you wanted to, see how it affects things. You can try disturbing some of these constructs here and see how you can change things. There's lots of interesting things that can be done within this game, but most fundamentally, it shows how very simple rules can cause very complex, in fact, computationally universal behavior. Okay, game of life. It doesn't give too much insight into life itself, other than you don't have to look for very complicated explanations for complex phenomena. Sometimes the explanations that are needed for a complex phenomenon are profoundly simple. Profoundly simple. You can see very complex patterns out there in the world, but the explanation comes down to something very, very simple, straightforward. And so this is an illustration of that general principle. Stylized model meant to give a high-level insight rather than to try to predict something specific. It's fun, but we're going to move on. Okay, game of life. Let's go explore this a little bit, shall we not? Okay, so let's go see what's going on. Go click on cell. A cell here is very, very simple. They've chosen to depict this in a particularly sort of basic fashion. So this variable here is a Boolean variable. It's true or false. And it starts being true with a probability of 0.1. And there's a function here, a function that actually goes and evolves this in a way that reverses its current state. More to the point, though, if you go look here, there's actually a description associated with each cell for how it evolves. And this description is in discrete time, meaning it's in steps. It's not things are changing in a gradual way over time. Things can happen at arbitrary points. Everything moves in lockstep. All the cells update conceptually at once. They have a current state. They actually figure out what they're going to do next before changing anything. You don't want one to move before the other to cause some arbitrary ordering issue. They figure out what they're going to do, and then they all change at once, conceptually. Could change it a way that doesn't affect the others' change in this round. So here, just before a step, we go through each of our neighbors, and we count the number of neighbors around us that are alive. And this is a bit of code here, which computes whether we're alive in this next round. So whatever our alive status is, now we take the and of that. So if we're not alive, what is this going to be definitely? It's going to be, if we're not alive, if alive is false, what is this whole thing going to evaluate to? False, because it's alive and this thing. So if we are alive, we're only going to remain alive, we're only going to compute a value if the number around us is between 2 and 3, or, oh, excuse me, and I should have, this or is actually around this entire thing. So if we're not alive, if the number alive around equals 3, then we do become alive. I won't go into this in detail, but if you puzzle through the precedence of this, what it enforces is if you're not currently alive and you have a number around you that are 3, you become alive. If you are currently alive, the only way you're going to stay around is if the number around you is between 2 and 3. Okay? Okay. So this is a game of life. This updates it based on a value that was determined in this on before step. So first, all the agents, all the cells figure out what they're going to do, or how many are around them. Figure out all the information needed to change. And then when it comes time to change, they can change in any order. It won't affect the change in others because they have all the information already. Okay? So this is a discrete time model associated with sort of an abstract depiction of biologic processes. Very stylized, much more so than most of the models we work with, but sometimes you can get high-level insights from this. Okay, let's go see where the space is put, because part of this lecture is about spatial embedding. Let's go to main. Scroll down in main here. If you scroll down in main, what you'll see is that in main, there's environment for other agents. It says to divide space up. The width of the space is 500. The height is 500 units, 500 pixels. But the number of columns is 100. The number of rows is 100, meaning that it's broken up into cells essentially of 5 by 5. Why 5? Where do I say 5 from? Yeah, number of pixels divided by the number of say, columns or rows. 500 pixels across, 500 columns, or 100 columns across. Each of them is 5 pixels. Okay? You'll notice that it says arranged, meaning they're all lined up in kind of rows and columns. And the network type, well, it says user-defined, but the more important thing is neighborhood type. This is a more. Okay. So it's a more network. The other choice is Euclidean, where it only has 2 neighbors. No, sorry, 4 neighbors, north, south, east, and west. So Euclidean would consider these, north, south, east, and west. More considers all 8. Okay, so that's a little example of a cellular automaton. Cells remain fixed, they're either living or dying, and the focus is on the patches. Questions about that? Okay, we're going to go on now to look at a model also in a grid, but which exhibits mobility. It's not technically a cellular automaton in the same sense, because you have agents moving around between cells. The focus is not on the cells; it's not on the spatial components. It's instead on the agents. So, ladies and gentlemen, let's close. You can close the game of life if you'd like to, or you could keep it open if you'd like to play with it. Okay, I'm going to close it up, and I'm going to load in a separate example model. This one, ladies and gentlemen, is another stylized model, and it has also been highly influential. Okay, so go to example models, go down the right-hand side, and you see there's a model called Schelling Segregation down here. Okay? Schelling Segregation. In the example models, click on that, and it will load it in. Okay. And if we look at the broad features of this model, go to main, for example, folks, scroll down in main, you'll find that, like the previous model, it's divided into rows and columns. You notice it's a discrete space, discrete is specified here, and it has 100 rows, 100 columns. It's only 400 by 400, so each is 4 by 4. Okay? However, in contrast to the last one, now we have other agents. We have agents that are mobile, other types of agents that are mobile. And that's a person agent. So these persons can move around. They move around, however, in discrete time, meaning they move around in steps, okay? And we can see that if we scroll up in person, we'll see some rules. We'll come back to these rules later. I don't want to get too distracted by them. But let's go run this simulation and see what we see. Okay, so each person here is embedded in space. Each person has a certain color. This person, yeah. This model also originated in the 1970s with the sociologist Thomas Schelling. And Schelling was interested in the emergence of segregation within U.S. cities. Does anyone know what is segregation? Sorry? Yeah, creating separate areas for people with different characteristics. Race is a very common one. That's the one in which he was focused, and you'll see that reflected here. But you also see income segregation, education segregation. There's an element of homophily. People who have similar characteristics will tend to group together, right? And this model tries to capture that, and it tries to explore the degree to which that could arise through certain types of processes without presupposing extreme prejudice, just sort of slight preferences to live with other people like oneself, because language is easier, what have you. So let's click on this button, and what we'll see is that space is divided into a set of patches. In each of these patches, ladies and gentlemen, is associated with one of three possible states. So the first state that you'll see is it could be white or beige. Here that indicates an empty, it's unused space. There's no one living there right now. By contrast, it could be black, in which case it's occupied by an individual whose color is black, or it could be red, indicated that it's occupied by someone whose color is red. These colors are not representing particular ethnic groups. They're not representing a specific ethnic group empirically, some specific ethnic group in the world, but instead they're representing different ethnic groups. Red, black. Who knows what it represents? Here it's very stylized. But you'll notice that they're broad patches. They're broad sort of expanses which are in one group or another. When we first start the model, and I'd suggest that we use this little control here and gosh, I would have thought it would be displayed with this. The execution control would display time scale. That's what we want. I'm sorry. It's this time scale here. So you pull this down, you do time scale. Let's slow this thing down a little bit. Instead of having it run flat out, run it at speed 1. How did I do that? This was checked, uncheck it. And you go to speed 1. Do people see that? Okay. And now if you run it, you'll notice people start in a very intermixed state. What's happening? They're moving around. They're moving around according to certain rules. People who are colored red choose where to move to. People who are colored black here choose where to move to. And you'll notice what's happening over time. Can anyone describe it? Let's speed it up a little bit. What's happening? I'm sorry? It depends. This is stochastic, so you won't have exactly the same results unless you have exactly the same sequence of pseudo-random numbers given. So here it's probabilistic, do I move or do I not? I have a certain chance of moving, and that chance is higher if I'm in a situation where I would prefer to be with more people of my type, okay? But it's probabilistic. So here, we'll see these patches emerging from this kind of sea of original individuals. We'll see these patches as people move. They vote with their feet. They move to others who happen to be near them. So initially, they're very intermixed, but by this process of individual movement, choosing where to live, who to live next to, you can get these broad patterns of grouping, broad patterns of segregation. Now, it turns out that this slider up at the top indicates how much people prefer being with other agents of their same color. If you drag it here to the right, for example, you'll find that with larger assumptions, people tend to group even more so. And so we could speed this up, and you'll get, okay, at some point it becomes too much, and nobody's satisfied, and they'll never actually settle down. You move it down a little bit, you'll get grouping, and there's actually a critical threshold, the tipping point, where it'll go from having a very large number of people sort of grouped together to a situation where it's impossible. People are constantly moving and there's no settling down. By contrast, down here on the lower side, you'll get less grouping together. As you pull this parameter up, you'll get more and more emergence of this sort of grouping being okay. Okay, I think it was something with this Bluetooth. Let me make sure that's still, yep, it's still good. Okay. Why do we see that empty space? Anyone? Yeah, it's borders. And it's representing the fact that people of one group prefer to live near those of the same group, and by implication less those nearby. So they'd like to group with theirs, but not be next to ones of this other group if possible. And so where possible, they have this kind of border around them, whereby they're not mixing directly with others of their group. So let's go see the rules by which this accumulates and that governs this. Okay. So if we go look at these rules, let's go to person, and these are the code. And I don't expect everyone here to follow all aspects of it, but here, what we're doing is, well, can anyone from CS background help understand what does this code do? We're looking at person, and we're looking at their, anyone? They have a variable, it's a Boolean, true or false, whether they're satisfied or not. What does this code do? Those for computer science background, can you figure it out? Exactly. And under what conditions will they be satisfied? What factors would factor into it based on this code? Good. Exactly. If they have no neighbors, they're okay. If they have neighbors, how many of those neighbors are of their same color? That will be a key factor. So if they have no neighbors at all, they're satisfied. If they have neighbors, you figure out how many of them are the same color. And then we're satisfied only if the number of same neighbors forms a certain fraction, this threshold of our total number of neighbors. Neighbors.length. Okay, and then on step, what happens? Can anyone describe that from computer science? What is this? What does that operationally do? Okay. A certain probability of 0.3. Pick one that necessarily is better, they just jump to it. And obviously this could be This could be embellished. You could say, what would happen if people aren't satisfied with being around no one? Well, how would that affect things? Or what if they only move to neighborhoods that are more preferable in their assessment? Or what if they only knew about neighborhoods nearby them? Or what if they only know about neighborhoods in which their family members are located? You could characterize all that by elaborating the model. But right now, it's a very, very simple set of rules. Very similar to, but not identical, I think, to those from Schelling. Question? They move over the entire space right now. It's very interesting to have them only move locally, for example, but eventually they might diffuse over to areas they'd eventually get to anyway. So what do you think would happen if, for example, we were to change that threshold to be higher? What do you think would happen? Well, that's exactly what we were playing with before. So if we ran this, we were making them in a way more intolerant by moving them to the right, demanding a larger fraction of their neighbors to be their same color. And at some point, it got too much to satisfy. They were never satisfied, and they're just moving around in this kind of entropic fashion. If they are satisfied, if they don't need any particular fraction, if they're not particular about their neighbors, who their neighbors are, you can have a very mixed sort of neighborhood. Very, very mixed sort of neighborhood. But, once you start getting up to a significant fraction, let's say 50% or so, they want at least half their neighbors to be people like them. You start to see real patterns emerge, real patterns in terms of grouping, in terms of these higher level constructs, which could at a high level be interpreted as kind of a segregation pattern. The more demanding more and more they prefer things, the more pronounced those segregation patterns become, until a certain point where they will be unsustainable, where they won't be able to be satisfied. Does that make sense, people? Okay. So this is the Schelling segregation model. This was originally played, just to give you to help you put this in context, the impact of computers in terms of understanding this phenomenon. This is of considerable interest to sociologists. I know a sociologist who works a great deal of her time looking at extensions to this model, and I've met whole groups where they're really, really interested in variants of this model, because it does represent one aspect of grouping behavior of individuals, of homophily. And it probably has some bearing. People like to have other people near them speak their similar language, have similar customs. So it's a very attractive model. But when this was first built by Thomas Schelling, it was actually simulated on a checkerboard. He actually ran it on a checkerboard by hand with pennies. I think it was heads and tails. And he did it manually to move things around. You can imagine how much, thinking about thinking prostheses, thinking about thinking tools, you can imagine how helpful it is to be able to change a parameter and rerun this and see the results within seconds rather than within the span of an entire day with those pennies. So these stylized models that are in the range of 40% or what have you, you can still, or 37%, you could still see quite significant patterns emerging of grouping, of segregation at a certain level. So some segregation unquestionably is the effects of residential steering. It reflects biased lending practices by banks. There's a whole set of institutional and opportunity structure considerations that go into real-world segregation. But modest preferences on the part of individuals can lead big patterns. It doesn't take necessarily huge racial, hugely racist ideas, but even sort of modest preferences add up to yield grouping that's very macroscopic, that's very obvious. Okay? So this is an example of another stylized model that that can lend some insight even into real-world phenomena. Okay, questions about that? Okay, okay, ladies and gentlemen, I think then we will put away our discrete model hat, and we're going to go on to look at some continuous models. So I'm just going to, well, I guess I'll continue on here. Okay, good. So there's more information around this. I want to talk a little bit about this issue of time. This is important. So, ladies and gentlemen, we've just seen two models, the Schelling Segregation model on the one hand, and this game of life, which operate in discrete time. All the agents operate in lockstep in many of these models, but it occurs in a set of steps. And so agents move at certain defined times, as it were, in the tick of a timer, the tick of a metronome. They move. And in these two models, they sort of all consider whether to move or whether to live or die at the same time there, which is very common. This sort of discrete time. Things are divided into these fixed length steps. And that's very common. By contrast, many of the models we were using before, most notably with system dynamics, with stocks and flows, with state charts, they make use of continuous time, meaning time is divided as fine-grained as it needs to be. Some things in the model may operate more quickly than others, but conceptually, time is a continuum. It's as divided as finely as needed. So we'll have a rate, a chance per unit time going from X to Y, and maybe it's in a state chart, and agents, some agents leave more quickly, some take longer to go. Some go within 0.01 time steps, some take 100 time steps to go, and the full range is selected. So we see for agent-based models and for system dynamics models, quite a few models that are continuous time models. Now, there's some real trade-offs between these. Can anyone give here a reason that you might want to characterize things in continuous time? Well, let me ask this. If you only had a discrete time model where you do it in steps, could you simulate everything that you do in continuous time?
Arbitrarily small steps.
Okay, arbitrarily small steps. Good. That's right. Either that or you have steps of a fixed size and you kind of figure out, you broker, okay, so this thing may have happened within the past year, this other thing happened, which of them happened first? And you handle them in that order, sort of figure it out that way. If you have continuous time, dividing things up as fine-grained as possible, it's very natural for describing things in the world, because the world tends to operate in quite, you could argue at a femtosecond, sub-femtosecond level if there's somehow time quantization, but there's not a lot of evidence for that. In other words, it seems things are pretty continuous, certainly for all practical purposes. And you can capture real-world phenomena quite crisply by just allowing certain things to happen more often than others and at a finer-grained level. Some processes operate very, very quick clock, as it were, some is slower, but you're not fixed to some fixed time steps. If you do have fixed time steps, you can't actually simulate these phenomena. It's just you do so either with very fine-grained time steps or within a time step, you kind of, after the fact, broker, okay, what happened before what, and give that priority. Okay? So discrete time, you can characterize things. It's often a little bit more awkward. Why would you prefer, for those with a computer science background, this is a very subtle issue, but, and you folks are probably third year, some maybe fourth, so it's possible you would have seen this. Why might you prefer sometimes discrete time? Why discrete time? Why might you prefer that? In a way, it's easier to grasp. In a way, it's kind of straightforward. You think, okay, so that has some truth to it. For certain people, it's easier to grasp. How about another thing? Sorry? Yeah, there's actually more mechanism needed there. That's right. You have to have what's called, and we'll come back to this later, event handler or continuous a scheduler, something which, and we call them discrete events. They get handled at arbitrary times, and you have to go through each event as it's going to be handled, and handle it at the right time. And you can do that. But it requires more mechanism. There's an event queue that you have to get into, and it needs to handle it. So scheduling these things can be more complex, more mechanism. How about another thing? Well, in terms of parallel processing, the ability to process things concurrently at the same time. It turns out it's with discrete time, you might treat all things within that time step as being able to occur concurrently, so you can map them out to different processors or different computational units. And that can be very advantageous for processing speed. Very plumbing issue, technical issue, but you should be aware there's advantages either way in terms of implementation, some in terms of concepts. So it's not at all obvious that one is totally dominant. Right. Important point in discrete time, you don't want the behavior elicited to depend on the order, the vagaries of the order, who went updated first. You don't want the behavior of the whole model to be dependent on is agent A updated before agent B consistently, or vice versa. And so it's very common here that you might do this, what we saw in those two models. Each agent, before doing anything, before changing anything, they figure out what they're going to do. They collect all the information from around the agents around them before any of those agents have changed. And then, when they're actually going to go update themselves, none of the other agents around them depend on them. So they can update that. We can update in any order. Plumbing issue, but an important one from the standpoint of implementing this and having a model in discrete time. Okay? And this is a little bit similar to what we saw in system dynamics. The changes over the next little bit of time in system dynamics. What are those changes dictated by in a system dynamics model? By the changes are captured in the flows. Thank you. Thank you. And those flows are calculated from what? From the stocks right now. But the flows are all determined from the current value of stocks, and only then are the stocks updated. And because the flows have already been determined, which stock you update first doesn't matter. Plumbing, but for those from computer science background, it's an important consideration. So here we have this on before step, on after step sort of distinction. Okay. So we can enable discrete time in the main class. There's this enable steps, which will enable these kind of regular steps for agents or for the main class. Okay. Okay. So we have this on step and on before step, right? Okay. So we ran this model. Okay. That's great. I think we're going to finish with a little bit of fun. We have about 5 minutes left, and this is going to get us started on some things that you're going to be working on before next lecture in terms of just watching a video. So ladies and gentlemen, I'd like you to create a model here. File, new, here, file, new, model. And I'd like you to click this model and call it Simple Mobility 394-858. Note that I'm continuing to post these things. You don't have to call it the 394-858, just to remind me. Simple Mobility, okay? So I did, again, File, New, and then Model, and then I did simple mobility. Okay? And I'd like you to open that up. I continue to post these models to the website. Okay? And ladies and gentlemen, I would like now to create a little model which is going to exhibit some behavior. So, ladies and gentlemen, I'd like you to remind me, how do I add an agent class to this model? Okay, go to project, right-click here, do new agent type, right? And we'll say person. Okay. Okay. How did we do that? Right-click here, new agent type, and we said person, and then it did finish. So person, and then finish. Okay. 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 So we have this person. We're going to give them a representation, and this time we'll put in, just for the sake of it, we'll go down here and put in, down to this palette area, we'll put in representation that shows them as a person. There we go. Okay? I have a feeling not everyone will hew to my description there, but some people may have other types of agents. Okay. Great. And then how do we create a set of these agents in space? Remind me. Go to main, drag this in, okay, and we'll say it's a population, okay, a population of agents, 100 agents, okay, and how would we lay them out so that they're randomly spread across the space? Okay, main, where would we look? Yeah, advanced down, excuse me, what am I doing? In main, go click on main, and then you could scroll down to environment for other agents, and you're going to say layout type random, which related to that question earlier, okay? Ladies and gentlemen, what should we see if we run this right now? What's that? Yeah, a bunch of people sort of sitting around, right? Okay, great. Okay, ladies and gentlemen, I'd like you now to do something that you're probably not expecting, which is go to the presentation area here, and I'd like you to draw a rectangle over the space. So how did I do that? I went to presentation, I dragged up a rectangle here, and I enlarged it so it occupies much of the space here. Okay? Okay? Is that okay? Sorry? No? Okay. Okay. Starting at the origin, I did it, yeah. Okay? Okay? Okay, great. So, ladies and gentlemen, I'd like you to, we're going to, watching the time here. Okay. Great. So I'd like you now to click on this rectangle, okay, and I'd like you to scroll down in the properties for the rectangle to where it says advanced, and open that up. Advanced here, okay, and specifically go to this on click, okay, on click, okay, and basically we're going to have it so when we click, they're going to move towards where we clicked, okay. Okay, so those from computer science background. Oh, this would be so much nicer in Java 8, which is now supported by AnyLogic 7.1. I wish I could do it in that. Oh, it would be sweet, but I can't because we're running the earlier version of AnyLogic. but this can be done in one line. It would just be beautiful. But we don't this. My computer is slow. For person P in the population, okay? Person P in the population, we want to do P dot move to, and you'll notice there's this little light bulb here that tells us something. And pay attention to those light bulbs, because they often tell you contextual information that's available. It says click X and click Y are the coordinates of the click. So we're going to move 2 through 1, but it's exhibiting truculence. So I'm going to be slow, but maybe that's good for you folks. Click X, click Y. Do you see that? For person P, colon population. For each person in turn in the population, calling them P, we're going to tell it, hey, P, move to the location X and click X, click Y. Where did that click X, click Y come from? Well, it was the thing that we were told. Okay. Sorry, it's hard for me to maneuver this. There we are. Click X, click Y. Okay? Okay, ladies and gentlemen, build early, build often. You can do this up here by doing this. Now, I'm going to put this up on a bigger screen, so if there's people trying to see it, you could see it more clearly. Can everyone see that? Yeah? Okay. Even in the back? Okay. Person P, colon, population, P dot move to, begin paren, click X, comma, click Y. Notice it's case sensitive, right?
What's going to happen?
What's that?
What's going to happen when you click on somewhere?
So what's going to happen, you're saying? So what's going to happen is it's going to do this, and what is this going to do? Anyone?
Any specified person or every?
It's moving everyone in the population. Let's run this thing. Ready? Okay. Oh, they're behind. Oh man. Sorry, folks. We're going to have to change the ordering. See this rectangle? Go click on the rectangle and do order send to back. Send it to the back. Okay. Okay. Yeah, you could do that. Thank you. Okay. So now we should see something like this, and there we go. What's going on? What's that? Yeah, they're moving towards the point where we're clicking. Their phase space is being compressed. Okay. This shows how you can get agents to move, exhibit mobility. Is this continuous or discrete, ladies and gentlemen? It's discrete. It's discrete movement. Sorry, what am I saying? It's continuous. It's continuous space. Ignore that. Oh, that's interesting. Arrival time. Okay. Ignore that. That's interesting. Okay. Ooh, wow. That's fascinating. I think my computer's acting up in some weird way. Okay. So here we have people moving around. What's happening? We're clicking on this rectangle. When we click on the rectangle, what's happening? Well, what's happening is this thing that we put in there in advance is running. For person P in the population, for each person in the population, it's telling them move to where I clicked. And that, ladies and gentlemen, is what you see here. They're moving to where I'm clicking, right? Now they're all moving to there. And notice they all move, I don't have to tell them, and there's going to be some exploration in the video that I ask you to send, where we move them on a schedule between home and work, or home and school, okay? But this is a quick examination of continuous mobility. Mobility over space in a continual fashion, where you tell it, move this person towards there, and it will start moving according to a velocity which you could set on a per-person basis, okay? This will be of help for some some of the video and for some of the problems. Okay, so that's all for today. Thank you for your patience. We covered a variety of types of material, stylized models, spatial embedding, elements of mobility. For the next time, I'm going to ask you to watch some more stuff on mobility, and we're going to be going on to some new material. Okay, thanks very much.